On March 11, 2011, at 2:46 p.m. in the afternoon, the ocean floor off the northeast coast of Japan moved 50 meters in 3 minutes. What followed was not a wave in the way most people picture a wave. It was a wall of black water, heavy with debris, cars, boats, houses, everything the sea had already destroyed further out, that arrived inland not as a breaking surf, but as a surge, a rising. In some places it reached 40 meters, in others it traveled 10 kilometers inland before it stopped. In 1 hour, the tsunami killed nearly 20,000 people. Japan had seawalls. That's the part the story usually skips. Along the northeast coast, the Tohoku region, communities had built concrete barriers for decades, designed exactly for this scenario. The city of Kamaishi had something more impressive than that. It had the world's largest breakwater, a structure so formidable it was listed in the Guinness Book of Records, completed after 3 decades of construction at a cost of $1.6 billion. When the 2011 tsunami arrived, it crumbled on contact. More than 1,000 people died in Kamaishi. Across the rest of the northeast coast, the picture was similar. Nearly 90% of the seawalls that existed before March 11th either failed structurally or were simply overtopped by waves larger than anything they had been designed to withstand. Japan's response was, in every sense, massive. The government committed over $12 billion to build a new coastal defense system unlike anything constructed before. 400 kilometers of new and reinforced seawall running along the northeast Pacific coast, built to heights of up to 12.5 meters, taller than a 4-story building, in some places taller than the Statue of Liberty's base. The project took years and involved moving more concrete than was poured in the construction of the Panama Canal. Workers built individual sections by hand where machinery couldn't reach, adapting the design site by site to the unique conditions of each bay and headland. By any measure of engineering ambition, the Great Wall of Japan is extraordinary. And by the assessment of some of the engineers who study these problems most closely, it may have created a danger it was meant to prevent. To understand the paradox, you have to start with what the wall was actually designed for, because most people assume the answer is obvious, and the obvious answer is not quite right. Japan's government did not design the new seawall to stop a tsunami like 2011. That event, a magnitude 9.0 earthquake triggering waves up to 40 meters in some locations, is classified as a once-in-a-thousand-years catastrophe. The ministry responsible for the project explicitly acknowledged that the new walls are not built to withstand something of that scale. What they are built for is the more frequent, smaller-level tsunami, the kind that arrives every 50 to 150 years. The logic, then, is not about stopping the water, it's about buying time. Engineers believe that in 2011, many victims missed survival by as little as 2 or 3 minutes. A wall that slows a tsunami, that reduces its initial speed and height, that creates a delay between the water's arrival and its full destructive force, could translate those 2 minutes into lives saved. On those terms, the seawall makes sense. The problem is what happens to a community that has lived behind a 12.5-meter concrete wall for 20 years. Nubo Oshuto, a tsunami engineer at Tohoku University who spent decades studying these problems, events put it plainly. There is simply no guarantee that seawalls will stop every tsunami. What he and other researchers are more concerned about is the effect the wall has on the people behind it. The presence of a large, visible, seemingly permanent barrier creates what disaster risk specialists call complacency, a slow erosion of the instinctive awareness that a coastal community develops over generations of living with the threat of the sea. If the wall stops the small tsunamis, people stop responding to warnings. They stay home when sirens sound because the sirens have always been wrong before. They develop, in the phrase used by multiple researchers in this field, a false sense of security. This mechanism was already visible in 2011, before the new wall existed. Tsunami warnings are frequent in northeastern Japan. In the days before March 11th, there had been a warning. People heard it, assessed it against their experience, and did not leave. Martin van Alst, director of the Red Cross Red Crescent Climate Center, has observed the same dynamic in the Netherlands. The public impression of safety is so high, they would have no idea what to do in case of a catastrophe. The better the wall looks, the less people feel they need to know what to do when the wall is gone. Yoshiaki Kawata, a disaster management expert at Kansai University, said something more direct in the immediate aftermath of the 2011 collapse of Kamaishi's world record breakwater. This is going to force us to rethink our strategy. This kind of hardware just isn't effective. But the engineering concern goes further than complacency. It goes to what happens if the wall fails. A standard tsunami arrives at a coast and spreads its energy across a relatively wide area. Water flows in, water flows back out. Destructive, catastrophic, but physically distributed in the way that unobstructed water tends to be. A seawall changes this physics. It acts, for as long as it holds, as a dam, holding back the volume of water that would have otherwise have spread. And if that wall fails, or if the water overtops it, the result is not a dispersed flood. The water concentrated behind the barrier releases at once in a torrent that can be more violent and more focused than the original wave would have been. Critics of the wall noted specifically that several sections of the pre-existing seawalls in 2011 appeared to have worsened the flooding behind them when they gave way. The Kamaishi breakwater, even as it crumbled, may have channeled the water in ways that concentrated its force on the town behind it. The new wall is higher and stronger than anything that existed before, but it is not infinite, and the waves that exceed its design parameters will not politely stop at the top. The higher the wall, the more water it can hold back, and the more potential energy it contains if it breaks. There is also a subtler engineering concern, one that plays out not in a single catastrophic moment, but over decades. Building in areas protected by a seawall has historically led to increased development in those areas. More buildings, more residents, more infrastructure built on the assumption that the wall holds. If the wall fails, the losses are larger than they would have been without it, because more is at stake behind it. What saved the most lives in Kamaishi in 2011 was not the $1.6 billion breakwater. It was a civil engineering professor named Toshitaka Katada, who spent years before the disaster training the town's schoolchildren in a specific evacuation protocol. Run immediately. Don't wait. Don't look back. Don't stop to find family members. Get to high ground. When the earthquake struck, the school students in Kamaishi did exactly what they had been trained to do. Most of them survived. The adults who hesitated, who paused to evaluate, who trusted the wall, many of them did not. The Japanese word the tsunami research community uses for this principle is tendenko, a Tohoku dialect word meaning roughly, run for yourself, don't wait for others. Every person is individually responsible for their own evacuation. It is not a comforting philosophy. It runs against every instinct to protect the people you love. But the data from 2011 and from previous Tohoku tsunamis supports it. Communities where tendenko was practiced had lower death rates than communities that tried to coordinate collective evacuation. No concrete wall teaches tendenko. A concrete wall, by its presence, argues against it. Fudai is the counterargument. A small village on the Iwate coast, it sits behind a concrete floodgate built in the 1980s by a mayor named Kotoku Wamura, who had survived the 1933 Showa Sanriku tsunami as a child and was determined that his community would not experience it again. The gate was condemned at the time as a costly boondoggle, ugly, expensive, unnecessary. In 2011, it held. The wave rose behind it and receded. Fudai survived with no deaths. But Fudai's wall was built for a wave height based on the 1933 event. Had the 2011 wave arrived at Fudai's location at its worst intensity, even that gate might not have held. Japan spent $12 billion on a wall that its own ministry acknowledges cannot stop the scale of disaster that prompted its construction. The engineers who built it say it will save lives. The engineers who study tsunami risk say it might, over time, cost them. Both statements can be true at once. The sea has no opinion about walls. it will arrive again at a height and speed determined by geology, not by concrete. When it does, whether the wall helps or hurts will depend on something engineers cannot design and governments cannot mandate, whether the people standing behind it in that moment decide to run. If the hidden engineering logic behind how societies try to protect themselves, and sometimes succeed and sometimes don't, is what you want to understand better, stick around. And let me know in the comments, if you lived in a coastal town in Japan right now, would you trust the wall?